So greetings, welcome to week 5, and today we'll be solving a few problems relating to the Hurwitz-Routs criteria, and we'll also take a look at one problem on PID controller. So what is this Hurwitz-Routs criteria? It allows us and it helps us in figuring out whether the roots of the polynomial, right, it allows us to figure out the nature of roots of the polynomial. So we can use this criteria along with our transfer function, the notion of stability, to figure out whether the system is stable or not. So let us work out the criteria with these two example polynomials. So in the first one, the polynomial is given by this. If we construct the array, it's a third uh, degree polynomial. So s cube, s square, s power 1 and s power 0. Then we will arrange the coefficients as s cube coefficient is 1, s square coefficient is 5, then we have this 2 as coefficient of s, and finally 12. Now let's compute this coefficient here. We'll be using these four numbers to do that. So so the denominator is this term here, 5, and then we do this multiplied by this minus this multiplied by this. So 5 into 2 is 10 minus 12. So this equals to minus 2 over 5. So let me rewrite it appropriately. Minus 2 over 5. Then we use these four entities. So here there is nothing, so we will take it as 0, and we multiply minus 2 over 5 into 12 divided by minus 2 over 5, that results into 12. So let us count the number of sign changes. In the first column, so there is one sign change here when we go from plus 5 to minus 2 over 5, and there is one more sign change when we go from minus 2 over 5 to 12. So such number of sign changes in total are 2. So what does this imply? This implies that there is there are two roots of the polynomial in the LHB and one root in the RHB, right, left half of the complex plane. And since there are sign changes, this also implies that this polynomial is not a Hurwitz polynomial. Similarly, let's take a look at the second problem. S power 4 plus 3s cube plus 6s square plus 12s plus 8. So let's construct the array. So here the first term is 3 into 6 minus 12 into 1 over 3. So that would be 6. Oh, my bad. Yes, 6 into 3 is 18 minus 12 over 3 equals to 6 over 3, that is 2. Then we take this as 0 and we go 12 into 8 minus 6 into 0. So that would be 8. Now for this position we have 2 into 12 minus 3 into 8 over 2, which is 0. So since this term would go into the denominator when we calculate the next term, we cannot divide by 0. So let us replace this 0 with some small term, small number epsilon, which is greater than 0. So this becomes epsilon into 8 divided by epsilon, which is 8. So since we said that this epsilon was positive, there are essentially no sign changes happening in the first column. Since epsilon is positive, there are no sign changes on uh, in the first column. This implies all the roots are in uh, LHB. Now coming to the next problem, the control system should ensure closed loop stability and satisfy some performance criteria. Consider the second order plant governed by y double dot of t plus 4 into y of t is equals to u of t. So if we take Laplace transform and substitute 0 initial condition, we get s square y of s plus 4 into y of s is equals to u of s. For the transfer function, say g of s, or let's call this as P of s, since its Planck transfer function P of s is 1 over s square plus 4. If you quickly look at poles, this will be s is equals to plus or minus 2 iota. So this is complex poles on the imaginary axis. So here we are expected to try out different controllers P, I, D, PI and PD and check which of these stabilizes this particular system. So let us start with first part, a P controller. So for such a controller, C of S is Kp. So G of S, which we had previously defined as P of S into C of S, is Kp over S square plus 4. The closed loop transfer function was given by G of S over 1 plus G of S into H of S. Now let us assume unity feedback, so H of S is equals to 1. The closed loop transfer function in this case would be so let's just yes, so since the closed loop transfer function is coming out to be this, its poles would be plus minus under root of Kp plus 4 iota. This implies the poles are on imaginary axis. Since the poles are on imaginary axis, we cannot conclusively call this system as a stable system. In the past, we have discussed this as or this to be referred as a marginally stable system. So the proportional controller alone cannot stabilize this system. Now let's come to the second portion, integral controller. So in this case, C of s would be Ki over s, and G of s, which was P of s into C of s, becomes Ki over s cube plus 4 s square, 4s. So looking at the closed loop transfer function, it is again so we are assuming a unity feedback here. So if we were to take a look at the routes array, we have 1, 0, 4 and Ki. Since we are having this as a 0, the denominator polynomial is not Hurwitz. That is, the roots, or rather the poles of the closed loop transfer function are not completely in the left half of the complex plane. Hence, the integral controller alone cannot stabilize the system. Now let's try the derivative controller. So the C of s is Kd into s. That makes G of s as P of s into C of s. So the closed loop transfer function in this case, G of s 1 plus G of s into H of s. Now we have uh, this has the closed loop transfer function. If we write routes array for this, one kd and 4, and if we calculate this value here, it will be kd into 4 minus 0 over kd, so that would be 4. So here, if kd is greater than 0, then there will not be any sign changes in the first column. uh, of the routes array. This implies a derivative controller can stabilize the given plant. Although, if you remember, uh, using a derivative controller alone is not recommended generally, because the derivative controller can amplify the noises in the input, and hence cause the system to have some issues. Now let us work with the PI controller. C of S is Kp plus Ki over S. So this is Kp into S plus Ki over S. Now writing the closed loop transfer function here, Kp into S over Ki divided by S cube plus Kp plus 4 into S plus Ki. Now if we check the routes array for this polynomial, since there is this 0, the polynomial is not Hurwitz. So the PI controller cannot stabilize the system. Last is the PD controller. Now the E of S for PD controller is given as P plus KD into S. So the G of S, which is P of S into C of S, is written as KD into S plus KP over S square plus 4. Closed loop transfer function now is given as again assuming the unity feedback KD into S plus KP, and the denominator it's S square plus KD into S plus KP plus 4. So here we have 1 KD KP plus 4, and if we write it, I'll write the last term here, that would be KD into KP plus 4 over KD. So KD will get cancelled and we'll be left with KP plus 4. So this is the first column, and so to have roots of the denominator polynomial in the LHP, KD should be greater than 0 and KP plus 4 should be greater than 0. This implies KD greater than 0 and KP greater than minus 4. So if we were to draw a region denoting Kp and Kd, Kp should be greater than say minus 4 in this side, and uh, Kd should be greater than 0. So if I were to shade, so this is a stable region. So this thing is called as a controller parameter space, where the controller's parameter Kp and Kd in this particular case form the axes, and a portion of this space corresponds to the region where the closed loop transfer function is stable. So this is an extremely important and powerful tool. So if in case you are supposed to figure out a search problem, right, in which you don't know what kp and kd values should be chosen, and you have plethora of objectives to satisfy, you can restrict your search region in the stable region itself, so that all the solutions you are looking for, or all the solutions you are obtaining, are essentially stable solutions. Now coming to uh, the second portion, the closed loop system is designed to have settling time below 1 second and have maximum peak overshoot below 15 seconds. Report the range of damping ratio and real part of the poles that satisfy this performance criteria. So here we are given uh, two different criteria to follow, and we have a closed loop system. So from what we have learned, we'll consider a second order, a general second order system, that is our p of s is omega n square over s square plus 2 zeta omega n s plus omega n square. Now we are required to have maximum peak overshoot less than 15%. So the maximum peak overshoot is given by e power minus zeta pi over under root of 1 minus zeta square. This should be less than 0.15. So if we take log on both sides, we'll have minus zeta pi this implies zeta over and if we just try to figure out value for zeta, that comes out to be 0.5169. So this is our first condition, which ensures that the maximum peak overshoot is less than 15%. Now we also want our settling time to be less than 1 second. So Ts, assuming the 2% criteria, was 4 over zeta omega n. This should be less than 1. This implies zeta omega n should be greater than 4. So if we can combine both of these to figure out the value the range for omega n as well. Then we are asked about the real part of the poles. This is minus zeta omega n. This is, from this inequality we can write as less than minus 4. So let's consider one more, let's take a look at one more problem. Here we will try out a proportional controller assuming unit negative feedback and figure out again what mm, and try to figure out controller parameter space. So the governing equation is given by y double dot of t, thus say 3y dot of t minus 2y of t. So if we take Laplace transform with 0 initial condition, get s square y of s plus 3 into s y of s minus 2 into y of s equals to u of s. So our plant transfer function p of s y of s or u of s becomes 1 over s square plus 3s minus 2. So if we were to use a p controller, the g of s would become p of s into c of s. This is given by now let's write the closed loop transfer function. So if we were to write routes array for this again, the final term would become 3 into kp minus 2 over 3, that is kp minus 2. So to have for stability, kp minus 2 should be greater than 0. That means kp should be greater than 2. And if we so I think that's all for today's tutorial. Do you have any questions?
Can you please scroll up to the proportional control in second question?
In the second question, huh?
Yeah,
uh, yes.
so KP can be positive or negative.
Yeah, right.
So it can take values of plus or minus one, right, to stabilize the system.
Okay, so let's see. If it is say -5, which looks very convenient, okay, uh, what would the poles be?
Oh, sorry, sorry.
It will be,
On real life.
yeah, one will be on the left hand side, other one will be on the right hand side,
Right, right.
right? So, yeah, so in this particular case, the poles are on imaginary axis, but if Kp is say greater than 0, uh, it would be on the either side of the imaginary axis, right? Yeah. Oh, any other questions?
Yeah, in route 7, you whenever it's zero, you assume epsilon is a small positive
Yeah.
real number. Uh,
So you want to try it here?
no, it's just a random but is there any uh, I don't know why are we restricting it to being a positive? Like, won't it have any effects if we assume it to be negative as well? Like, how can we just eliminate the possibility?
Uh, Good question, of which I don't know answer. But let's try it out as an experiment. If we take that epsilon to be negative, we'll end up having two sign changes. So I think it's
Yeah,
better to. I'll get back to you with some textbook references with this regard, and in the YouTube video, I'll probably put it in the comments of where we can read up more on route sharing.
all right.
I don't know the answer to it as of now.
Yeah,
All right.
that's it. Thank you.
Yeah. Thank you. So I think let's close the session. Thank you for joining.